Oh, you did?
Today we are going to learn physics measurement terms. Among these are precision, accuracy, parallax, and we're going to learn how to identify a sig fig and how to round correctly. Hooray! Some people think that precision and accuracy are pretty much interchangeable terms, but they are not. They are complementary terms. They work together in dealing with measurement, but they are not the same. Precision is how detailed a measurement is, which is dependent on how many marks a measuring instrument was made with. All good measurements should have one digit more precise than the smallest marking on the measuring instrument. On the other hand, if we're dealing with accuracy, it's how correct a measurement is, which is based on how well the instrument was made and or how well you use it. And all good measurements should contain one and only one uncertain digit. That should have helped you fill in a couple blanks, but so far a lot of that probably just listened like blah blah blah. So we're going to give you some examples. Here we have a very exciting box.
It's a present.
Here we have a box. We are going to measure our box, and we are going to measure our box with
this.
Isn't it beautiful? Is this precise?
Yes.
No. Precision deals with what? What's our keyword? Detail. Is there a lot of detail there?
No.
It says 1. That's a lot of detail there, man. 1.
So I can tell is it bigger than a meter or smaller than a meter. This box is going to be smaller than a meter, so we know that one. Okay, so over here I'll make a little chart. Here we're going to have our smallest mark, and here we're going to have our measurement. Okay, so we have our smallest mark in our measurement, and we'll add to that as we go on. This one, the smallest marking is
1.
not very detailed. Now, is it accurate? Well, it says 1. Would it lie to me? I don't know. It might. How can we tell if it's accurate? Accurate is how correct it is. So how do I know if it's correct or not? Do I just have to have faith? It was made by
Canadians, and Canadians are the metric, eh?
So that must be good. Is there another way we could find out? We could measure it. Here I have 2 meter sticks that are made by 2 completely different companies, and I put it against this meter stick made by a third company, and they're all the same length. If they're all the same length, then we can either assume that there's a vast worldwide conspiracy to mislead us, which I'm sure there's several of you. Yeah, man. Okay, anyway, it's probably accurate. If 3 different companies say it's a meter and they all agree, then it's probably really a meter. So we can assume that the accuracy is pretty good here. And I'm using it, so we assume that it's being used properly, right?
Right?
Right. Okay, so we now say this is not very precise, but if I stick this up next to this, how many people would bet your life that this box is smaller than 1 meter? There's a couple of you that are like, no. Okay, so we would bet our lives that this is smaller than 1 meter. So it goes to like right here. How much into 1 meter is that? Okay, I have to write this number down, man. So I know for sure it's 0 point something. What am I going to put for the something? Everybody just rate it? I might be wrong, man. I can't take the pressure. Seriously, nobody has a number.
35.4.
Okay, we have 0.4, we had a 0.35, 0.45.
.4,
0.45.
0.45,
0.48.
0.48,
A continuous point.
0.41, 0.39,
A continuous point 33.
0.33333333.
Yeah.
Okay, I heard a couple of these that were good, and the rest of you need to get slapped.
Sorry.
No, not yet, because you haven't been trained properly yet. So after today, you'll get slapped. Here's the deal. When we're trying to get this number, the 0 we were willing to bet our life with. We knew it was less than 1, so it's going to be 0 point something. The something part, I heard some people say 4. I had some people say 4.1, 4.3, 4.9, 3.3. You start adding these other things. How many of you are going to bet your life on the 0.4? Seriously? I'm going to kill you if you're wrong. Okay, a couple of you are very bold. If you're willing to bet your life on the 0.4, then you can go farther. But realistically, what do we have to do to get the 0.4? But there's a special word for that kind of measurement. I don't see a number there. I have to estimate. What is an estimate? Yeah, in middle school they teach you that an estimate is an educated guess. That sounds like a guess that went to college. But I don't like the word guess because I want you to guess a number between 1 and 10. I'm thinking of it right now. What is it?
4, 8, 4,
3.
Okay, what numbers did we hear?
7,
8.
I heard pretty much every number there is, right? Now, when I said, how far is this to one number, what am I going to get? 0.4? Is anybody going to give me something other than 0.4? Okay, so, again, was that a guess? If everybody came up with the same number? Okay, when I said guess a number between 1 and 10, you guys weren't cheating and saying, it's going to be 3. Right? You just went with something. So 0.4, it was a reading. You were looking at this and you said, well, it's not quite half, so it can't be 5. It's a little less than that, so it's probably 4. So that was a pretty safe estimate. Now, if I switch from this ruler to this ruler, is it more accurate?
Yes.
No, the same people that made this one made this one. Right? So it is no more correct, but it is now more detailed, so it is more precise. Yes, now we have how many markings on it?
Say 10.
So now it's 0.1 meter is the smallest marking. So now if I stick this up to here, I find that it's just a little short of right to there. So now would you bet your life it's 0.3 something? Yeah, and all those of you who were betting your life it was 0.4 are now dead. Because that number was really 0.3 something. What is the something if it's right here?
8.
Okay, again, was that a guess or was it a reading?
Reading.
That's clearly a reading because the only two numbers I heard were 8 and 9.
8, 5.
I'm not going to bet my life on the 8, and 5 is just junk. So you can't do that. So here, the smallest marking, I'm going to say it was 0.39. Now, if I said it's 0.39 and you say it's 0.38, can I slap you?
Me.
No, I cannot. It makes me very mad. I cannot because that last number is an estimate, and all estimates contain uncertainty. So if it's uncertain and I say it's a 9 and you say it's an 8, I can't say you're wrong. Now, if I say it's a 9 and you say it's a 3, then I get to slap. So it's great. Okay, so now we're going to switch from this ruler to this ruler. Did I just get more accurate?
No.
Good, you didn't fall for it this time. Again, the same company keeps making all of these, so this one is more. Now we have how many markings? Say 100.
100.
Hey, it's 100. So now my smallest mark is 0.01. So I know for sure it's going to be 0.039. I don't know. It's got to be 0.0. So here I go to here and the 40 is showing, but the 39 is covered up, man. In fact, I'll draw you a little picture. That was good. Okay. Yeah. Stop it. Yeah. Okay. Our little drawing. If this was the 39 and this was the 40 and there was a little hash mark in the middle just to help you out, the box came to right about there. So it's definitely 0.39. And then we have a something. How many people would bet your life on the 0.39? I do. It's clearly past 39. It's not the 40. I can bet my life on that one. No, he's hiding the ruler from us. Okay, so this one goes a little past half, so it's probably a 6. But again, you might think it was a little closer to 5, or you might be googly-eyed and think it's 7 or something, but we've got that going. Now, if we look at this, what we've done here is we should be able to look at this and say, hey, do these words have more meaning to us now than they did 10 minutes ago? Precision is how detailed the measurement is, and it's dependent on how many marks the measuring instrument was made with. When my smallest mark was 1, I could go to 1 pass. When I was 1 pass, I could go to 2 pass. When I was 2 pass, I could go to 3 pass, which means, hey, all good measurements are 1 digit more precise than the smallest mark on the measuring instrument, because that extra digit was an estimate, so it contains some
Uncertainty.
Thank you. So here is how detailed it is. Notice how each of these measurements is getting more detail. In the case of numbers, more detail means farther past the decimal. So this one is more detailed than that one is. Accuracy, on the other hand, is how correct a measurement is, and that's based on how well the instrument was made. If this was a well-made instrument, then I'm going to get good readings out of it. But again, I also have to use it right. If I hold it like this, I can get real precise reading. I can say, oh yeah, that's 61.3. But is it right? No, because I'm not using it right. So I have to do it correctly to get that to work also. So it's based on how well the instrument was made and how well we use it. All good measurements, of course, contain 1 and only 1 uncertain digit, because I want to bet my life on every number except that estimated one. Capiche? Groovy. Moving on. A friend of mine invited me hunting. I know you're shocked. He has a friend. I did once. And one time he called me up and he said, hey, Paulson, let's go hunting. And I said, great, go pick me up. And I went and I got my rifle and I stuck it next to the front door. And then I went into my kitchen and I grabbed some munchies and I came out. And my rifle had been knocked over and was being sat on by my 2-year-old. That's what 2-year-old boys do. He was in no danger because my rifle was unloaded and locked up and all nice and safe. But how many of you would like a 2-year-old to stomp on your scoped rifle? Why would this be a bad idea? Ideally, the scope and the barrel are very precisely aligned. And when small children start jumping on it, you start to doubt that. And so I said to my friend when he picked me up, hey, I'm not sure if my rifle is shooting straight. He said, no problem, we'll go out to the ranch and we'll shoot at a target before we actually go hunt. So we get out to the ranch and we set up a target, and we paced off 150 yards, and I sit out there, and I aimed right at the center, and I squeezed off around, and I looked at the target, and I thought I saw a little spot down there on the lower left. And I said, I don't know, I might have hit it or it might be a bug. So I cut another shell and I aimed right at the center and I squeezed off another round. And I said, man, I must have missed entirely. So I aimed at the center and squeezed off a 3rd round. And I said, man, I don't see anything. And then I said, I got to go check and see if that's a bug or if I actually hit it that first time. So I walk up to the target And I look at this little spot that looked like a bug, and it wasn't a bug, it was Mickey Mouse. I had shot all 3 bullets through the same hole. So the question that you at your table group need to decide on, was my rifle accurate, precise, both, or neither? Okay, by now, ideally, we have come to a consensus, and most of you have. There were a few people that were still, So, what was my key word for accurate? Correct. What would be the correct spot I was pointing this gun? The correct spot was right there. Where was I hitting?
Right here.
Is that correct? So that was clearly not accurate, and so that pretty much kisses off both also. Now, what was my key word for precise? Detail. Now, what would be detail in shooting? Hitting the same spot, or at least a nice tight group. Was this a nice tight group?
Yes.
You can't get much tighter than that. So yeah, that was very detailed shooting. So that means it was precise. Then once I readjusted my scope, of course, it became both. Well, at least when I shoot it. Well, seriously, you give it to some people. I have a friend. He always has me sighting his rifle because when he takes a group, he'll have one here, a one here, a one there. What is he? Accurate but not precise. They're going pretty much where he's pointing them, but they're kind of all over the place. I like to get a nice tight group. It's much more fun. So, if you guys like to shoot precisely, what's fun to do is you fill up a soda can with water and you put it out at about 150 yards and it looks about that big. And you shoot that, and when you shoot that with a large caliber rifle, that much energy hitting the water wants to escape through the top, but of course it can't, and so it just goes, and you get this really pretty piece of aluminum that's all very unique every single time. They're kind of cool looking. So, something to try. Parallax is our next word. Excuse me. Parallax is a sighting error, and so that is going to affect my measurements.
Just learn 2 words. One of them goes in the blank.
Precision.
If it's an error, that should affect our accuracy because that means it's going to be not correct. We don't like that. So let's pretend that this meter stick is a speedometer. So you're sitting in your car and it's a red light, and so the needle's over here, and then the light turns green, and you go. And now you're going this fast through the little elementary school zone. No, don't drive like that. So how fast am I going now?
It looks different from us.
I'd like to say
Some of you are getting very wiggly all of a sudden. Am I not holding it high enough?
60.
What do you mean you can't see? You got a clear view?
It's not touching.
You don't see the pencil go across the ruler at all from your point of view. Well, not if you keep wiggling your head. How come everybody keeps wiggling their head?
Because it's not always on.
Yes, what's happening is you guys are trying to avoid parallax. You've been trained to do it your whole life, you just don't realize this is the word that goes with this. But realistically, you know that the best place to take a reading would be where? Right in front of it. So everybody at this front table was like leaning in, doing all this stuff. Some of you over there were getting real anxious and you're doing some leaning stuff. Some of you were dying to get out of your chair, but it was just a second hit. I don't know if I could do that, man. Some of you were just like, I can't do it, man. So you were just quitting. But in reality, you can take a reading from where you are, right? So what do you see this going across?
50.
50? What do you see?
63.
63. What do you see?
65.
75?
70.
70. Okay, now, were there any differences in the precision of those readings? Everybody gave me a 2-digit number, right? Nobody said, oh, that's 63.927. Somebody else said, oh, I can only see 70. Right? It wasn't that. So it wasn't that detail that we were having trouble with, but could all of these numbers be correct? No. So we were affecting the accuracy of this number. Now, who would be most correct?
People saying 60.
Probably whoever is most perpendicular. What do you see, Morris?
60.
Really? Okay. I see 60.5. I'm more detailed. Okay, so one way to avoid parallax is you want to get as perpendicular as possible to your instrument. You learned this in chemistry class. You had to read a graduated cylinder, and they told you to read to the bottom of the meniscus, but they also told you to read from eye level. Why would you not want to read from the top? Why did you want to get down at eye level to read? Because we're avoiding parallax without reading. The other thing, of course, we could do is, if I stuck this right here, would people have much of a problem? No, no matter where you're sitting now, unless you're sitting behind, then you're going to say, oh, that's 61, or maybe that's 62, but you're not going to get farther off than that, so you're going to get pretty close. So you want to get these as close as possible to each other. If you have that happening, that also can eliminate parallax. So if I'm trying to take the reading of something with a meter stick, the problem is when I have a meter stick, like say I'm using this one, the meter stick itself has thickness. So if I'm trying to read the width of this thing, it matters a lot where I'm looking. It can vary quite a bit. But if I stick this on top of that, am I going to get much of a difference? Here the scale and the object are actually in contact. Here, they got this much space in between them. So it depends, the parallax will really mess you up. Here, not so much. So there are different ways that you can use your instrument to be more accurate. So parallax is not always evil. Experiment. Hold out your finger like this. Stare at the wall past your finger. Close one eye. Switch eyes. Switch. What did your finger do? It did not move. Your finger is in one spot, but it looked like it was doing a little dance, right? If your finger looked like it was doing a little dance, that was because your eyes do not see from the same angle. So one eye is over here, the other eye is over here, and so they see from a slightly different point of view. That's helpful to us. If you watch my eyes, I'm going to watch my finger, and as I watch my finger get closer and closer and closer, I get more and more cross-eyed. So things that are close, my eyes have to do this, and when they're farther away, they get closer to parallel. By knowing how far in and out my eyes are going, that's sending a signal to my brain telling me how far away something is. So if I want to throw a rock at your head, it's much better to do this with two eyes than one. If I just have one eye, you're much more likely to get away. And, I want to hit you. I sound so violent, right? Thank you. So parallax can be a friend there. Significant digits or significant figures, they're interchangeable terms, are numbers that have actually been read. And of course we know that the last digit was estimated, therefore contains some uncertainty. So if we're reading somebody else's numbers, we have to know which ones are measured, which ones were uncertain. And there are some rules for that. Let's pretend we think the population of Laredo is around this number. It's bigger than this. I wrote this a long time ago. But one person writes it down this way, another person writes it down this way. If we look at these numbers, there's different assumptions that are built into the numbers. If I look at this first number, which number do I think is my uncertain digit? Probably the 1. The way we write this down, we say, hey, this 1 is uncertain. That 1 could be a 2 or a 0. And so really I'm saying plus or minus 10,000 people when I write it down this way. If I write it down this way, what's my uncertain digit here?
7.
The 7. The 7 could be a 8 or a 6. So here I'm saying this is good for give or take 1 person. So am I transmitting the same number basically? If I promised you this much money and I gave you this much money, would you say, oh no, that's way different, man? You'd be fine with it, right? So it's the same thing. We are expressing approximately the same number, but we're telling you different meanings behind it. Now, does population always stay the same? So which one of these is more detailed?
209.
Okay, so the second number is clearly more precise than this one is. Which one is more accurate? We don't know unless we know what the actual population of Laredo is. So let's assume for a minute that we could freeze time and we run around, we count everybody in Laredo, and it turned out to be this exact number. And then we let time start again. Once time starts again, how long will this number be accurate? In the city our size, probably 20 minutes. We got people born, we got people dying, we got people moving out, we got people swimming in. It's a joke. Anyway, I live like a quarter mile from the river, so anyway. On the other hand, how long is this one going to be accurate? It's give or take 10,000 people, that's probably going to be good for a couple years. So there's different meanings behind the numbers that we write down. And so that we're transmitting that differences by the way that we write it down. If we're going to, let's get carried away there, Paul. If we're identifying significant digits, there are a couple rules that go along with this, and most of these rules are so common sense that you're never going to have trouble with them. Guess which one you're going to have trouble with? Hey, number 3, notice how I put little stars next to that one to call your attention to it. So the first one just says everything that's not a 0, count it. If the 0 is in between numbers that are not zeros or numbers that are significant, then count it. down here in number 4, it says if it's in scientific notation, everything up to the x or the e is significant. Number 5 is just a cleanup rule. It says everything else is not significant. But number 3 is the one that's a little bit tricky. What do we do with zeros? So the rule is any zero that's both to the right of a significant number and to the right of a decimal is significant. What this comes out to is dealing with how do I deal with zeros at the beginning and how do I deal with zeros at the end. Zeros at the beginning, very, very simple rule. Beginning zeros how often do we use beginning zeros? Never. Never, 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 never. Beginning zeros, never significant. So this one would be 2. On the other hand, we look at this one and we say, well, zeros at the end. Zeros at the end, it depends. This is the one that we have to look at. This one we never have to think about because they never count. This one, we look for a decimal. If you do see a decimal, it does count. If you don't see a decimal, it don't count. Yeah. We'll pretend Miss Arciniega didn't hear that. So, yeah, we'll make it even worse. If we do see a decimal, it do count. If we don't see a decimal, it don't count. I'm trying to emphasize the... Okay, anyway. So in this number, would they count? No. The 3 and the 2 would be significant. The 3 zeros would not. Now how many would be significant? All of them. If I see a decimal, then all of these count, which means I measured it all the way out to there. That's my uncertain zero. Does this make sense? So this is the rule to remember. Beginning zeros never, ending zeros. If you do see a decimal, it do count. If you don't see a decimal, it don't count. Boy, I sound educated, don't I? So let's try some. Our first number, how many of those are significant?
6.
All 6, what's my uncertain digit?
7.
The 7, which could be a 8 or a 6. How many of these are significant? All 5, even these zeros?
Yes.
Yeah, because they're in between other numbers that are significant. My uncertain one is the
3.
3, which could be a 2 or a 4. If I have 149 billion or trillion. Billion. Okay, so that would just be
3.
because I
What happens?
don't see a decimal. So now I have 246.30. Does the 0 at the end count? Yes, because I do see a decimal. So my uncertain digit here is the 0. That could be 0.29 or it could be 0.31. If we have 1.47 exponent 13, does that mean I have 13 sig figs? No, it's everything up to the x, which means I have, and my uncertain digit would be the 7. Now we get to 0.0003270. Lots of zeros, man. The ones at the beginning never count. The one at the end, only if I, which I do, so it. So my uncertain digit here is going to be the last 0. Any questions on those? This will follow you through the entire semester to make sure you do understand. How can you show that the number 128,000 has 4 sig figs? In other words, when I measured this number, I estimated that my digit was exactly on the line. This first 0 counts, the other 2 do not. How can I show that to you, man? I'm so confused. There's 2 good ways to show it. One would be if this had a unit behind it, like if this was in meters, I could say, hey, that's just 128.0 kilometers. Did you see what I did there? Tying into yesterday's lesson. How clever! Or the other way to do it would be I could stick this into. Whoops. Thank you. If I put it into scientific notation, now you look at everything up to the E or the X and you say, hey, that would have 4 sig figs in it. Get it? Those are your 2 best ways of doing it. Any other way is really cheating and may not be understood everywhere. But those two are good. Last thing is rounding. Why do we round? How many uncertain digits can we have? One. But the problem is if I use uncertainty in multiplying or adding to other numbers, then that uncertainty carries into my answer. And what happens is that uncertainty can magnify. Now we have a problem. All good measurements contain one and only one uncertain digit. But we have numbers like here, 11.3 divided by 7.28, and your calculator will hand you that mess. So the problem is when you were a little kid, you learned how to add and subtract and multiply, and then somebody handed you one of these. And you started going, these are great, I don't have to think at all anymore. And yeah, my son, when he was like 5, he used to pick up a calculator. He'd go, hey Dad, what's 123 times 987? And I'd go, I don't know. He'd go, I do. Like he was so smart. The problem is you get so used to these that sometimes you type in something and you hit a button by accident and you don't even notice because you have total faith in your calculator. What happens is your calculator has gone from being a tool to becoming your calculator God. And you're like, yes, calculator God, thank you for those answers. I never would have made it through math class. Thank you. You're such a benevolent God. So when he hands you all these numbers, you look at these numbers and you say, they must all be good. He's a good God. He would not give me bad numbers. But in reality, some of these are good numbers and some of these are just a waste of your time. You have to know which ones are which. To do this, we have our rounding rule. Now, if I'm multiplying or dividing and adding and subtracting, they're a different rule because a different process is happening in that uncertainty. If we add and subtract, the rule is we're going to round to the least precise digit. And when we multiply and divide, the rule is to round to the smallest number of significant figures. These sound similar, but I'll show you how they are actually different. So least precise is worried about where the decimal is and how far past it we are. Smallest number doesn't worry at all about where the decimal is, it just counts. If we are adding, if I have these two numbers and I added, the calculator will just spit this out. Now, what's my uncertain digit in the top number? It's a 7. This 7 could be a 8 or a 6, which means this 7 could be a 8 or a 6. Now, in the second number, what's my uncertain digit? The 3. This 3 could be a 2 or a 4, which means this 2 could be a 1 or a 3. So when I add them down like this, how many uncertain digits do I end up with in my answer? 2. But how many should I have in a good number? Just 1. So you're not going to want to sit every time and do little circles and do it by hand. That's going to be a pain. So we have this rule. And the rule is I round to my least precise digit. And again, precision is how much detail we have. So how far past the decimal? How far past the decimal is my first number? 3. How far past the decimal is the second number? 2. Which one of these is least precise? 2. So the least precise digit is 2 past the decimal. So if I look at this, I say, hey, 2 past the decimal, that's going to be right there. But of course, you use normal rounding rules. So you say, I look past it, and if this one's 5 or bigger, then this becomes a 3. So the calculator guy hands me this, but I say, forget you. I'm going to slap him and say, no, it's 17.23. He's lying to me. He's giving more precision than I really want. Does this make sense? Do you see why this rule works? Okay. We go on to multiplying. When we multiply, we do not look at how far past the decimal. We just look at total numbers. Because if you remember doing this the long way, if we had 42.7 and we're multiplying, this is uncertain and this is uncertain, right? That means when I say 7 times 5 is 35, carry the 3. 7 times 2 is 14 plus 3, 17. And you're doing this, but every time this 7 is touching one of these numbers, then all of these numbers are going to be circled, right? Because that had uncertainty, so all those had uncertainty. And then when you're working with the 4 and the 2, not so much. So what happens is, again, you're not going to sit there and do the circles all the time, but if you do the circles a couple times, you're going to say, hey, there's a pattern I see. And the pattern I see is just counting. So how many total sig figs does the first number have?
6.
It has a total of 6. The second number has a total of 3. Between those two, which one is smaller? 3 is smaller than 6, so my answer can only have 3 sig figs in it. Now, if my calculator is handing me a number that I can just drop it past the decimal, no problem, you drop it. But sometimes the calculator God hands you a number like this. If it hands me a number like this, I only want to keep how many of these? 3, not 3 past the decimal, but 3 in total. So if I have 3 in total, do I just say, okay, that 5 rounds that 2 up, so I'm going to give you 843. That would be wrong, because if I promised you this much money and I handed you that much money, you would be very upset. Right? On the other hand, what I'm saying is I can only keep 3, so I want to go and stop at the decimal to keep it the same size number, but I can only keep the first 3 numbers, so that rounds up, which means that turns into a 0. The other way you could show that, if that freaks you out too much, is again, you can stick it into scientific notation, and you say I moved it 1, 2, 3 times, and you could write it that way. So whichever one makes you more comfortable. But if you're past the decimal, if the number came out to like 8.2479394, then you just say, okay, I'm going to stop at this one. This one's going to round that to a 5, and all those just drop. But if I haven't hit the decimal yet, everything until the decimal turns into an uncertain digit. There's no decimal, so that 0 does not count. So that's it. For homework, guess what? Problem B. That starts where it says B and ends when it says C, which means the entire front page should be done by next time, because C doesn't start till the back. So everything you see from B on down is going to be your assignment for tomorrow.